Good afternoon, ladies and gentlemen. My name is Mark Pryor. I'm the head of the Scientific Methods Unit at the International Data Centre here in CTBTO. CTBTO's waveform station network, seismic, hydroacoustic, and infrasound, is truly global. And yet, only our hydrophone stations are deployed on the seabed, even though the ocean covers more than 70% of the Earth's surface. In recent years, humanity's appetite for communication has resulted in an enormous effort to connect continents with fiber optic cables. More than 1 million kilometers of cable are carrying signals around the world, even as we are talking here. There is an exciting possibility that this vast network of cables could be used not only to carry information, but also to gather information about the natural world. Techniques have been developed to extract from these cables data about earthquakes, underwater sound, and ocean conditions, without interfering with the cable's normal operations. In the future, cables could be routinely deployed with sensors built into their structure so that every new connection provides a new opportunity to better understand our world. This panel, which I'm proud to introduce, will discuss this fascinating project. I'm pleased to say that it will be moderated by Dr. Charlotte Rowe, who is a research seismologist with specializations in waveform signal processing and event detection methods, tomographic inversion, and precise event location. She began her career studying volcanoes and has applied both seismic and hydroacoustic methods to nuclear explosion modeling. She serves on the International Joint Task Force for the Science Monitoring and Reliable Telecommunication Cables, otherwise known as SMART cables. Charlotte, the floor is yours.
Hello? You have to be in the microphone. There.
1, 2, 3.
Okay, there we go. Okay. Hello, welcome everybody to this panel discussion talking about seafloor cables, seafloor sensing, and the complementarity of individual sensors versus some of the cable sensing techniques where they use the actual cables. I believe the best way to proceed right now is, I think Mark has done an adequate introduction for me. I have been on the Smart Cables JTF for about 9 or 10 years now, and have been doing some global modeling associated with how much we could improve our propagation models to improve event detection and location using the seafloor cables as additional sensors to augment our land-based arrays. And what I would like to do is we'll go down the line, and each one of our panelists will be able to introduce themselves and tell you a little bit about themselves. And then once we've done that, we'll come back, and we have a number of questions that we hope that the expertise of these fine gentlemen will be able to provide you with some insights into this exciting new realm of seismology and hydroacoustic sensing. So we will begin with Andreas Wüstefeld.
Yeah.
Okay. And so please introduce yourselves to us.
Yes, hello. I'm Andreas Wüstefeld. I work for NorSAR, which many of you probably know as the Norwegian National Data Center. I'm the technology lead for fiber sensing at NorSAR since 2020. I have a background in global seismology and also earthquake oil field seismology. Yeah, much of the work, my early work was on seismology. and I have general interest in signal processing, event detection. And since 2020, I work on the fiber sensing at NORSAR. And to me, fiber sensing is a very fascinating technology. I initiated then in 2023, some of you may have heard about the Global DAS Month, which is basically a big push in the seismic community to leverage several deployments. We recorded for about 1 month every teleseismic earthquake around the world. There were 32 organizations collaborating to that. The data set is freely available, so it's a great way to get into DAS research, basically, and we have all kinds of different data sets available, offshore, onshore, borehole. So the idea behind there is to see what can be done, how can the seismometer network be augmented. And at NORSAR, we contributed with our Norfox fiber array, which you see here on the right-hand side, bottom right. It's a fiber cable basically deployed in this kind of wheel pattern, co-located with with seismometer arrays, so we can there really nicely experiment and find out, calibrate dust data against seismometers and do all kinds of explosion monitoring research.
Thank you. Next, I'd like to move on to Mikhail Masur, who is with Nokia Bell Labs. And Mikhail, can you tell us about yourself?
Yeah, thank you for the introduction. So good afternoon, everyone. I'm Mikhail. I'm with Bell Labs in New Jersey, where I focus on research dedicated to building fiber sensing systems, specifically focusing on extending the reach to cover the entire domain of our subsea cables. So as was mentioned in the introduction, we have this amazing network of something like 600 cables now connecting continents and countries. And while there are a lot of fiber sensing technologies out there, most of them are kind of limited in reach, leaving the deep ocean unmonitored. And my research is really focusing on extending that down in the deep ocean. So there is a few pictures there. For example, the one in the middle where we were able to do seismic monitoring almost 3,000 meters down, and this is about 1,200 kilometers offshore. So.
Thank you, Mikhail. Next, I'd like to introduce, or have him introduce himself, Hiroyuki Matsumoto, who is from Jamstack in Japan. So Matsumoto-san, could you please tell us about yourself?
Thank you, Charles. And hello, everyone. And first of all, I'm Hiroyuki Matsumoto, a senior researcher of the Japan Agency for Marine Earth Science and Technology, Jamstack. And first of all, I would thank the organizers for inviting me to the fantastic panel sessions. And I'm very honored to be here and share with our Japanese technological development in the ocean. This slide overviews the Jamstack research and development, which covers the global change and utilization of marine resources and marine geodynamics, with such as submarine earthquake and volcanic activities, computer sciences, and exploration for deep sea environment, and marine engineering. And there is another division which operates the research vessels and underwater robotics and large facilities, which facilitate our research and development. And our Jamstack headquarters is located near Tokyo, and there are 4 branches from north to south of Japan. And I'm belonging to the IMG division, and I'm involved in the sea floor of the batteries. Thank you for your attention.
Thank you, Matsumoto-san. Next, we are pleased to welcome Danil Karasov from LLC Ch1 Sensor in Russia. And Danil, could you please introduce yourself to us?
Thank you. My name is Danil. I am from Ch1 company, developer of DAS systems. So my main activity is in the field optical systems, electronics, and I have done several scientific publications about DAS systems and its application in geophysics and seismological tasks. That's all.
Okay, thank you. And finally, we are pleased to welcome Esteban Chavez from the Observatorio Volcanologico y Sismológico de Costa Rica. And Esteban, could you please introduce yourself?
Absolutely. Thank you very much for the invitation, and thank you to my fellow panelists that are joining this great discussion, and thank you to all of you for being part of the room today. My name is Esteban Chavez. I'm a seismologist, an earthquake seismologist. I study earthquakes in Costa Rica. I'm the current director of the Volcanological and Seismological Observatory of Costa Rica, and I bring the perspective of Latin American countries where we have these observatories and we need technologies, new technologies to monitor earthquakes and tsunamis. It is important to bring this infrastructure to growing economies and making more accessible to what we have. These countries are very prone to have important earthquakes in the past. We all know this story of Latin America, and especially the earthquakes and tsunamis that have hit in the past. So I will bring this perspective to kind of connect the story that we're going to try to build today.
Hey, thank you, Esteban. Now comes time for the pop quiz. And I've got a bunch of questions that I'm going to be directing to our panel, and we're hoping that everyone will jump in after the initial target has finished their say. Some folks will have technical slides that they will present in order to amplify their points or explain better their acronyms or what it is they're talking about with these new technologies, because we know it's hard to keep up. So first of all, the first question is to Andreas. And the question is that DAS has become sort of the talk of the town in recent years. It's actually been around for more than 10 years now. Some of the first publications came out about 10 years ago. But it has really taken off in terms of seismological observations and for waveform sensing of various sorts. And so, Andreas, can you give us an overview of the history of this technology and potential applications to the 3 IMS waveform technologies, potentially?
Well, yeah, I will try to stay brief here. But yeah, so DAS has maybe a long history. You have to go a bit further back, actually, to the 60s or 70s, when the first patents was actually released. And Michael actually just told me that the Bell Labs, it was in 68 or something, Bell Lab?
Yeah, there was a lot of early work, also by other labs around the world.
So it's been around for quite some time, the fiber sensing itself. To my knowledge, it then started actually off with temperature sensing. In the 70s, 80s, commercial systems were released. Vibration sensing, or distributed acoustic sensing for vibration sensing, then was basically in the 80s, 90s, just intensity-based. So you could get just the intensity of a waveform, but not the actual waveforms. So that changed dramatically with the introduction then of phase-sensitive measurement systems, and also when the oil industry actually in the early 2000s picked up on that technology. Lots of money was poured into that system in the early 2000s. Lots of development were done. Also in parallel then with development on the computing side, where computing power or the relevant computing power became accessible. So that also then helped to spur that, or to kickstart the developments. And basically since the mid-2010s then, this has become a standard kind of commercially available tool, and many more, many companies actually now offering commercial systems, which is good, so we have stability and availability and not just rely on one system. So that is good for, in my view, for the IMS system. So we have now a sort of proven system that the CTBT can then rely on. And to come to your second part of the question, what is the relevance to the IMS technologies? So we have, of course, the hydroacoustic, the seismology, and the infrasound system. I guess all of them can benefit from it is rather cost effective to use DAS systems on existing fiber cables. Michael showed in his introduction, and we saw it also several times before here, the ubiquity of fiber cables. So offshore, we have the long distance offshore fiber cables that connect the continents. So obviously that's great for the hydroacoustic to fill the gaps in the sparse hydroacoustic systems. Also on land, we can augment the existing systems, fill gaps, maybe also in the global south, where at the moment there's very poor or not as good coverage as there is in the northern hemisphere. So yes, seismology can benefit, and of course also the infrasound. We have seen at NORSAR quite some interesting results with infrasound being recorded on DAS systems, on buried DAS cables. That was kind of a surprise for us. So yeah, I think all of the systems can actually benefit from DAS.
Did you have any technical slides that you wanted to use to augment? No, okay. So yeah, I guess a couple of things that immediately come to mind, and we could probably all speak to this to some extent, is what are the main challenges that you see for these technologies with regard to the applicability? What are the problems that are going to have to be overcome in order to be able to regularly exploit these methods?
Well, maybe I start and then we go on. So I guess there's still a acceptance gap with every new technology. In my view, there's the believers and the doubters, and I feel that now there's a lot of papers in the academic out there to prove that this is actually working. And so the acceptance, we are getting there. We have to calibrate the systems against existing technologies. That's where maybe the array that I was showing earlier co-locate fibers with existing systems that will help to calibrate. And there's also the challenge of data storage and data transfer. It's producing a lot of data, but I think this whole community has overcome it. I mean, some of you in the room may remember the challenges in the 90s when the actual IMS system was set up, where there was a discussion on data transfer. How do we transfer all these lots of data from the seismometers? At the time, it was a lot of data to be transferred over the kind of internet. You remember maybe dial-up modems. That was the high speed of the time. So I think data transfer and storage will be overcome.
May I? Yeah. So Professor Jensen put the map before this panel showing the distribution of the cables around the world. And as you put it very well, most of the infrastructure is in the northern part of our planet. The global south, the coverture is not as good, though. Nonetheless, it is enough to start doing something. And some of the challenges that we're facing right now is, what are we going to do with the amount of data that these DAS cables are producing? We haven't figured it out. We haven't figured out a system where we can downgrade the costs also of deployment and processing of the data, because the computer power requires a lot. It is very demanding, and it costs a lot of money. So we need to reduce the cost. But I think this will come in the near future as the technology gets more acceptance and people start relying more on DAS.
Maybe I can. I think it's a great point. But I do think it's also important as a remark that when we're looking at DAS or the subsea cables, we're looking at the technology that scales with the telecom network. And I think you're absolutely right, and it's one of our big challenges. But I think from the perspective of this meeting, that is a general challenge we have, which is how do we bring more connectivity to the underserved parts of the world? And most of the times when I've seen successful, for example, DAS deployments, that comes because there is existing fiber infrastructure and we can kind of leverage that. And I think from the telecom perspective, one aspect of this is that a lot of the challenges you mentioned, to some degree, are solved with scale. like once you start scaling up and you're really looking at large-scale deployment, the costs come down, the cost of compute come down, like we have seen the cost of GPU. So I fully agree with the challenge, but I hope that by potentially working together and making sure we can do dual use of infrastructure, that might actually aid with the goal of bringing both, for example, seismic monitoring and connectivity to underserved communities.
That makes me think that one of the challenges is how to convince politicians and telecom companies to allow us to use the dark fibers, for instance, that they are not using. Most of these cables are not being used, and it is very expensive to, take the cables out of the ocean. So there is a great opportunity for scientists to use these cables. But we need to create strategies to, talk to them and see if we can use them at all.
Anybody else on this part of the question?
I can. About the data volume, usually we get information from every meter of fiber, and we get information every 1 millisecond. But it's too many information. For seismological tasks, we need 1 second, and not 1 meter. We can use 100 meters. So we can compress data one more decade in 200, 1,000 times. So, but usually we give all data. When I say we, I see people who made DAS, because we are afraid of lose useful data. So we decided to give raw data, and you can analyze it in any way you want. So, but when DAS become a tool, professional tool, we can compress data if we have a technical task.
Yeah, Matsumoto-san?
Yeah, I have a comment from the point of view ocean seismology. And the analyzing DAS data, we do using submarine cables. And we would like to understand the exact position, because the seismic wave is very sensitive. So, and so but the location of exact cable is not unknown or secret.
Yeah, this is an issue, yes. Andreas, the last part of this particular question, and something that I think every seismologist is certainly interested in, is what can be said about the absolute response of these systems?
Yes, so now you're getting into the hot topic of the day, talk of the town. Yeah, I think this is still debated quite strongly in the community. People are working on it. It's especially, of course, interesting for the magnitude determination. Location of events you can find out without knowing the exact response, but for magnitudes you need the transfer function. For transfer functions, you need to know the system response. How is the cable buried? How is it buried for each channel along the cable? How is the strain transferred from the buried soil to the cable, to the fiber, to the tube, so forth. So I think this is the biggest challenge if we want to calibrate the system for use in this community. And I think stations, or more experiments where we compare then the absolute responses and learn about it, that is needed.
Yeah, more work needs to be done.
Absolutely.
So, yes, we just need to geophone or hydrophone to calibrate it. But it's very hard to calibrate in every point. So when we change place, we need to do it again.
Absolutely. I'm going to move on to our next question, which I am going to direct to Mikhail. And that is, what applications do you see for other fiber sensing techniques, such as state of polarization, besides DAS, and for such things as, seismic, oceanography, cable health monitoring?
I think that's an excellent question. And from the Bella's perspective, this is something that we are trying to tackle in kind of a broad fashion. Actually, there is a slide up. So here, for example, is one of our work on really pushing seismic monitoring out in the deep ocean. And the reason for putting this up is really to say, I think, as Andreas said, DAS was around for a while, and all of a sudden got picked up. And there was an availability in terms of purchasing interrogators, lending interrogators, and so on. Specifically in the subsea domain, we have seen a little bit of a different journey where we started picking up, but there's been a number of different techniques investigated. So this goes from both polarization to phase-sensitive measurements, also to things like smart cables, dedicated observatories, and really understanding the balance between the telecom and the sensing as we go down in the ocean. What I think is important about it is that we were basically facing a duality of a challenge here. So the first one is that we need to maximize the sensitivity, and of course be able to provide as much useful information as possible. But I really think that the second thing is that in the subsea space, dark fibers are very rare. And subsea cables, at least until they expire, are very, very expensive. So it becomes these questions about compatibility. How do we make sure that we use the minimum amount of bandwidth to really enable sensing at a very low additional overhead compared to the datacom? And I think that the way we do this is also that we're trying to fuse as many sensors as possible. We try to make the best we can out of the cables. This is just one example here, extending 3,000 kilometers out in the Atlantic Ocean. There are numerous work like this, but it's not that powerful on its own. We have to remember that what we're trying to do is we're trying to build a complementary thing where we extract as many techniques from a subsea cable as we can, combined with all the land sensors and the decades and decades of knowledge about how to interrogate those sensors. And I think that comes back to what Andreas said, that most likely, especially when we're looking at reusing or dual use of infrastructure, this is not going to be the golden reference sensor that kind of seismology has been developing for decades. It's going to be an add-on that we can feed into the system and hopefully help to close the gap in some regimes. So the long story short is that I think we need to be very open-minded and investigate a broad range of techniques, not isolated, but together with the existing both seismic network and the knowledge within the various communities that we collaborate with.
Thank you. And this feeds right into the second part of the question, which I'm going to plow ahead, and then we can jump in on that. And that is, how do you see the complementarity between DAS or other cable sensing techniques and the smart sensors?
I guess I can start by trying to answer that. And I think this is a question we get quite often. And I try to tell people all the time that if you have the opportunity to put down sensors, always put down sensors. The more point sensors, the better. And I would be the first one to cheer if we started putting down much more dedicated observatories like the ones, for example, Jamstec operate offshore Japan. With that said, I think that fundamentally one of the challenges mentioned before and so on is that fiber sensing is a longitudinal distributed sensor. This is what we're operating with. And smart gives you the possibility to put point sensors, much more like our traditional sensors, along the cable while piggybacking on the datacom and the power management. So I think from a technology perspective already there, we kind of see the complementary nature of both of them. What I think is important is that we can hopefully, at least in my vision, try to use fiber sensing to fill the gap. Because smart sensors are likely co-located with the repeaters. So we're dealing with something, let's say 50 and 100 kilometer. And with fiber sensing, we can, in some areas, maybe increase the resolution a lot, pushing towards the kind of signals we observe on terrestrial DAS. So long story short, I'm not sure if anyone else has a comment on it, but that's at least how I see it. So I think they are both important and they're naturally a complement to one and each other.
Any other comments from other panelists on this?
Well, I like to think that when brittle failure occurs, radiates energy in a very broad frequency range, and this instrumentation is helping us to fill the gap between GNSS technology and a broadband seismic technology. We're kind of capturing the high frequency end of the signals, especially the tiny events that happen when the rupture is getting there before propagating. With this technology, we're going to be able to capture the premonitory phases that maybe lead to bigger ruptures. And that's very important for the future of the seismology and the rest of the earthquake science that is going to develop ahead.
Yeah, definitely the high resolution capability for the wave field might be particularly important for earthquake early warning, for instance, when you're in the nearshore environment. Yeah?
Yeah. If I may add here, I think I see DAS or SOP sensing, or it can be It is very similar to geophones, seismometers, but it's also not. Because we have this distributed system, we have lots of channels, we have the longitudinal array, we have very dense spacing that is different from seismometers. We have only a single channel. We have only a strain or strain rate. So some of our known equations from seismology that we know since 60, 70 years, they don't apply, but then they also apply because it's a waveform technology. So I think it's very similar to traditional systems, but it's also not. So it's filling an interesting gap there. So it is, a lot of research is needed there, and it will be fascinating to see how that develops and how that compares. So we need to compare co-locate basically cables with sensors to first learn about it, how we implement it. There's a lot of things that can be done already now, but to really do the groundwork science, I guess a bit more research there is needed, groundworking.
Well, this leads us logically to the next question. When we think about cabled observatories, everybody, of course, first thinks of Japan because they've got these brilliant cabled observatories for their earthquake location, early warning, and such. And this question says that Japan is leading the way on ocean floor observations for early earthquake and tsunami alerts. So Matsumoto-san, if you could respond to what role optical methods like DAS and other more traditional optical interferometry techniques in the future play in the future of these networks in terms of applicability, maintainability, and performance.
Thank you. And I would like to mention our C4 observatory development done by JAMSEC. And the DONET, the Dense Ocean Floor Network for Earthquake and Tsunamis, was conducted as project from 2006 to 2016. We installed 51 seismic and tsunami stations in the Nankai Trough seismogenic zone. And one of the features of DONET system is designed based on the modular type observatory, which allows to switch the sensor. Once the sensor happened to failure, the new sensor is attached by using an remotely operational vehicle, ROV. And after completion of DONET, we are focusing on the more precise or more higher resolution observation for detection of slow slip earthquakes, SSEs, slow slip events, SSEs, because the slow slip SSE is thought to be related to the megathrust earthquakes. Now we are operating 6 observatories in which the various sensors are installed. For example, seafloor pressure gauges and seafloor fiber optic strain based on the interferometry technique is to measure the horizontal and vertical and horizontal component seafloor deformations. And we installed tiltmeter at the shallow borehole by boring machine systems. And another one is a little bit expensive. We are operating 4 long-term borehole monitoring system, LTBMS, in the Nankai Trough. And the latest LTBMS was installed last year. And the latest one is we don't use the seismic sensor, but instead of not seismic sensor, but fiber optic strain meter, because we don't want to use the electronic devices into the borehole section, which may risk to failure. So this is an example of our recent developments. Thank you very much.
Thank you, Matsumoto-san. The next question, which is a really interesting one to me, is going to be directed to Daniel.
Yes.
And that is, can you give us some insights to how DAS and geophones are used for ice monitoring? In which regions and domains, sea ice, glaciers, and others? And how are these technologies applied?
Thank you for the question. I think that DAS and ice is very good in each other because ice has a good tension with cable. If we froze the cable, we have almost absolute tension of fiber. So it's very easy to calibrate it. So it's easy to compare with geophones. So I think that DAS will have great future with ice monitoring. And I have an abstract about this and article with a lot of details. We made a comparison with geophones, and we made multi-channel acoustic surface wave analysis and compared geophones and DAS data, and they almost the same. Also, there are questions about signal-to-noise ratio, of course, but anyway, DAS solve geophysics tasks, find a thickness of ice. So we can use it for such tasks or for another task, seismological or for another applications.
Has any of your work used seafloor DAS to observe the dynamics of the overriding ice sheet?
Could you repeat?
Have you used any DAS on the seafloor to make observations about the ice environment above?
We used DAS on the river, on the ice, which is covered river, so not near the sea, but I'm sure that it will work with sea as well.
Okay. Anybody else want to weigh in on ice?
No, I think I just want to say it's encouraging to hear the results, and from my perspective, that is one exciting potential thing that could come out of the changes in the global climate, meaning that we are actually looking at deploying substantially more telecommunication cables in the polar regions, both in the north and the south. And I mean, as we all know, these are very underserved regions when it comes to monitoring. So I think any work we do to understand the capabilities of these instruments can hopefully be leveraged to influence decisions to put more and more sensing capability of any kind of these cables, as these are cables that are still in the planning phase and have not yet been deployed.
Okay, thank you. I'm going to throw the last question out. We'll start out with Esteban Chavez. And this question is, how do you see these technologies' potential for tsunami warning? How do you see the potential of optical methods for volcano monitoring? Something near and dear to my own heart.
All right, I think the application is absolutely necessary. We have seen all the beautiful papers that have been published in the last years showing the results from DAS. Still, there is a lot to do, like calibration. We still need to calibrate to measure magnitudes accurately. But for DAS, I think I see a bright future. The more instruments we have in the field, the better, and we can more rapidly understand what is happening, especially when there is an earthquake, which is kind of the goal of the earthquake warning systems, is to have lots of instruments near the coast to capture the first waves that arrive to the instruments and send the signal to the observatories. With DAS, we will have the potential to have thousands of instruments in a very short wavelength. And so that gave us the capacity to improve the alerts, to reduce the time for the alerts, and improve earthquake hazard assessments, especially in the regions where there is more population developing. In volcanoes, for instance, I see a very good potential to measure tiny signals, the really small earthquakes that anticipate big eruptions, for instance, or tremors. the resolution of these instruments, I mean, the space or the interstation distance is especially important to capture the very small magnitude events that are happening that thus far we're not able to see. And so it's very interesting. I mean, I'm planning for the future to have DAS on volcanoes, for instance, in Costa Rica, where we will see the premonitory phases of those eruptions, or the premonitory phases of landslides. Landslides are very similar to ice in terms of the forming rates. And so right now we have learned, for instance, that before catastrophic ruptures, there are tiny events that repeat itself. The repeating rupture of asperities, very tiny asperities, but you have to be very close to the asperity in order to see it. If you move like 80 meters away from it, that's gone. The Earth attenuates all the energy. So I'm imagining the DAS, or a very nice cable throughout the landslide. And so we will be able to capture every single rupture of this fault zone before it catastrophically fails. I hope we don't lose the cable with the landslide though, but we will be able to have this beautiful resolution to capture the process before it happens.
I think replacing the cable would be a lot cheaper than replacing a broadband seismometer.
Yeah, I hope so.
I'd like to follow up on that a little bit. I worked for years at a volcano observatory, and of course our primary concern, as you say, was detecting the events in order to tell when something is cascading towards eruption. The calibration or the magnitude estimates were not as important as the earthquake counts. And so I could see potential for that. And have you thought about using them to try and capture some of the dynamics in pyroclastic flows?
In pyroclastic flows?
Mm-hmm.
Well, right now what we're using is just basic seismic instrumentations are implementing nodal arrays to capture most of the dynamics of volcanoes, for instance, but we haven't get into DAS. We need access to the technology, and the reduction of the cost is going to be a big issue for us because it will allow us to bring the technology to developing countries.
The logical extension of that would be snow avalanches, which can be in places as deadly as volcanic eruptions.
Yep.
Yeah. Anybody else have anything to weigh in on this? If not, we'll move to our questions segment. I've got some online questions here. I hope I'm reading the correct column. And while I am reading the online questions, that will give the audience an opportunity to build up their courage, formulate their thoughts, and come forward and get ready to ask their questions. So the first question from Anonymous. They're all from Anonymous. He's been very busy. What progress has been made in the global DAS month analysis? Has work begun on synchronizing some of the DAS locations? Has the data set been unified? I know this is an issue. They have different formats and different conversion standards and everything. So who would like to dive in on that?
Well, I guess that's to me. So yes, so the main aim of the Global DAS Month was first to bring the different organizations together and record the data set. We had a lot of discussions originally on how to homogenize the data set. It was then decided that it's actually beneficial to have a heterogeneous data set. So that was an active decision because then we have access to the different data formats and people can write like their internal processing software for the different data formats because that's what ultimately is available. There is a working group in IRIS that is occupied with this task, but as everybody knows in this room, agreeing on a data format is a challenge, and that takes time. There was also some initiative to homogenize the data set. That's always a funding problem, of course, and priorities. So I do know that there is a growing number of research publications now out with, they're doing work with the data set or part of the data set. So it is being used in the community, but as you also know, it takes time for this work to then get published.
Okay, thank you. Do we have any questions from the floor?
Also, I can add to the question.
Oh, yes.
We also participated in this experiment. So for manufacturers, we can compare our data. So we can compare signal-to-noise ratio of different devices. But because every time all data is under NDA, but this is open data, so we can compare, and we did it. Okay. So we know that we have a good equipment and compared to another companies, yes. So thank you.
Yeah.
And I know of a beautiful example in Chile where the University of Ch1 in France is deploying fiber optic cables in Chile. And they are recovering the data and processing the data. And I think they are storing the data in mini-SID format already. So it's a beautiful example of how you can process the data and make it available to the community already in formats that we know and have worked on.
Okay. Do we have any questions from the floor?
There are 2 questions.
Okay, yes, here's one, and Bruce. We have a microphone somewhere that moves around, or you can move to the microphone.
Thank you very much. My question is, how DAS is efficient to discriminate between two signals and a background noise from the ocean, for example, the animals, or any noise? Thank you.
Okay, thank you for the questions. For example, if about animals, they, for example, dig very quick or run very quick, so it's very different from seismological signals. But comparing to, for example, artificial sounds like cars, it depends on 2D analysis of DAS data comparing to the another one single point sensors. So it's a good point for DAS comparing to single point sensors.
Maybe I can also just try to add. I think naturally when we compare DAS to other sensors, we always end up in, or at least most of the time, end up in a domain where the SNR per sensor is much worse, but we have a much, much higher sensor density. So I think to some degree, largely the answer to your question lies in, we have to use the array-based processing to leverage all these sensors. If you extract a very few number of sensors, such as you would take a long telecom cable and put one DAS sensors every, 50 kilometers or something like that, I think it would be very hard to discriminate signals and do what you described. So personally, I think that the real power of it lies in array-based processing, leveraging the very, very high sensor density enabled by the fiber optic cable.
I believe we have another question over here.
Bruce Howe with Smart Cables. More comment that I'd like to compliment the panel on their great discussion and recognizing the complementarity of all the measurements. This community obviously is addressed with nuclear test ban issues, an existential threat to us, and the next existential threat is climate change. And so with smart cables and parts of the optical fiber sensing, we're addressing some of that. But I just throw out a challenge that a major user of this data from the climate perspective is the Global Ocean Observing System. And within that, there are roughly 20 essential ocean variables for the physics and comparable numbers for chemistry and biology. And so, there's huge opportunities to fill the gaps in those areas as well. And hopefully we can all work together to do that. Thank you.
Thanks, Bruce. Any response to Bruce? Or just an agreement?
I think it's an agreement.
Do we have any other questions from the floor? Yes, we do.
Good afternoon. Jelle Assing, KNMI. I was wondering about the robustness of the DAS systems. And because as we know, data outages is a problem. And we'd like to have continuous data as much as possible. Is this an issue with DAS currently, or are they very robust?
I mean, I can try to answer it. I don't think there's any general issues with reliability of DAS systems. Now, there are a bunch of different manufacturers out there. I think every time you scale up a technology, you do face the challenge of reliability versus cost. And I think the telecom system has shown it a lot, where at some point when you scale to tens of millions of units, you might even decide to say, okay, let's accept the failure because we have multiple backups and it's actually a cheaper solution than developing your golden unit. But I don't think the reliability of the DAS signals or DAS interrogators is a problem. And to some degree, I think because you inherently have a lot of sensors, the fiber also acts as a reference to your unit. So in my experience, finding errors, for example, on a laser, things like that, is actually quite straightforward, just because you have an unprecedented sensor density compared to point-based measurements.
Thanks.
Okay, I'm going to take another online question. Oh, is there somebody? Okay. Yes, please. It's really hard to see with these lights.
Thank you. Thank you for having this important discussion. My name is Tine Larsen from GEUS, the National Data Center in Denmark. The panel raised a very important question, which is a challenge to all of us trying to use DAS, the access to dark fibers, which is not trivial. And I think one key could be that we broaden our view a bit and tell the telecom companies that they can actually benefit from the analysis that we are doing when we get access to their cables. For instance, if we detect an earthquake on a cable, we can tell along the cable where is the cable well coupled to the seabed, where is it swinging freely, being exposed to wear and tear and eventually failure. So by telling the telecom companies that they can actually benefit from working with us, I think we might have a better chance convincing them that we as poor scientists with very low budgets should get access to all their wonderful dark fibers. So I don't know if any of you have any comments to that.
Can I try, as someone who's working for an equipment manufacturer? I think you're absolutely right. I do want to challenge the need for dark fibers, because I personally believe that dark fibers are not needed. And we, every day...
That's a bit old school, I agree.
Well, for us, I think it's also this thing that what you are saying is a problem that the telecom industry has been battling for a while. And I think in the public world, we often think of a telecom fiber as only carrying data, and there's no other signals present. That is not true. There is a substantial amount of monitoring going on within the telecom field. And as you say, the knowledge of the seismology and other communities about bringing this in and using DAS as a way to bridge this gap, I think can be very powerful. And it turns out that the actual DAS probes, as Andreas also mentioned, it's basically a phase-sensitive version of what the telecom field has been using for something like 3+ decades. So I think they're actually much closer. I do think that the biggest gap we're currently facing is that as long as we make the assumption of that we want dark fibers, we are very far away from each other. And I think by bridging that gap and actually accepting that we work together on live fibers, I know the bar is much higher, and the concept, like, people will tell you if you screw up. The feedback loop is very short. But I think that's really a way to take the two communities together and realize that we have a mutual interest and we can actually benefit largely by working together on this infrastructure.
If I can also add, so it was also mentioned before that the cable coordinates are actually a challenge for us. So we have to work as a community, I feel, also with the regulators and the cable owners and operators, that these coordinates, or the access to the cable, it's not just physical access, but it's also the metadata of the cable. All that kind of, there needs to be some regulation, or what is the access, how can we use that, so that there are some protocols in place of making those cables available. And if these dark fibers, lit fibers, or existing, I think that's everything, it's the same.
I think you're right, and maybe now I think Char will laugh, but I think that's also something that multiple industries are coming together where, for example, if you say that the coordinates of a cable are secret and you cannot publish them, but you can publish enough arrival times from different earthquakes, you effectively publish the coordinates of the cable. So, and I think that's a realization that is happening more and more now, that these problems cannot, as was told, just be treated completely independently. And I think understanding the mutual benefit from everyone by having access to this data, as you said, is fundamental for the regulators to actually make an educated decision about how to navigate the space.
I think the message here is that we need to show up. We need to get closer to the people that are taking decisions based on these cables, right? I mean, all the people that have the power of using the cables, telecom companies, governments, so on and so forth. So we need to show up and show what we can do with the cables and what are the benefits compared to the negative effects of using the cables. And that's closing the gap between science and politics. And I think is the most challenging part of all of this. Science is already done. We understand very well what to do with the data, with the cables, so on and so forth. But trying to add the social component to the scientific part that we're doing is the most challenging part.
And this all.
I can add. Also, I want to add that we can use not only dark fibers, we can use bright fibers as well. There are some techniques that allows us to use DAS interrogators using bright fiber. And we will not damage communication system, and it will work. Because sometimes get the dark fiber is much harder than to use bright fiber. Thank you.
I think this begs the question of another important topic. One more question? Okay, we have 2 minutes and 41 seconds.
Maybe I'm serving as devil's advocate, but I have one question, because I've seen a few waveforms for earthquakes with rather high magnitudes. So the question is, how do those DAS systems compare to the sensitivity of traditional instruments? Like, for the monitoring community, the music starts below magnitude 5. Because this is more or less we are looking for small events, not for large events, tsunami-genic events. So I would like to get some comments on that.
Well, I have seen examples of the network that the GeoZoo is deploying in Chile, for instance. They are capturing events with magnitudes below 0. So that's an example of how robust is the technology and how they can capture really tiny events with really good accuracy along the trench in the subduction zone. I don't know Japan how it's doing capturing the small.
Yeah, that is measuring the axis strain. So the discrimination between the contribution or between the glacier and seabed deformation is important to quantify the amplitude of tsunami at the sea surface, I think.
Okay, we are down to less than 1 minute. So if there's one more question that could be very, very quick, we can.
There's one question over here.
Okay.
Yeah, Birger Steen, I'm a colleague of Andreas's at Norsar. Just an observation, I spent quite a bit of my life in big tech, and typically the type of companies that the big telcos represent, they're actually quite eager to help with cost-effective things that make the world a better place if you address them on the right level. But my experience is that in the telcos, the knowledge of this technology is buried 6 or 7 levels down. And when you talk to a non-executive board member or a CEO about it, they typically fall off their chair. So to accomplish what you guys just described, I think the showing up in Mobile World Congress or other places where they meet and just telling the story, and Mikael, you have a day job in this business, so maybe you can be the spearhead, but showing up where these people are could help and go a long way, because the the network engineer isn't going to say, yeah, we're going to open up Vodafone's network to earthquake sensing, but their CEO just might.
Thank you. That's a very good point. And on that comment, I think we're going to have to wrap up. We're just a little bit over time. I'd like everybody to thank my panel for their wonderful insights and observations. And if you have additional questions, feel free to waylay them somewhere in the halls of the Hofburg and ask them your questions. Thank you.
And just to close off, I'd like to ask you all to show your appreciation for Charlotte as well for organising and moderating this very interesting panel. So that concludes this panel. We'll now hand over to my colleague Pierre-Yves, who will be taking us on to the second quantum revolution.
Good afternoon. So it is now time to go back to quantum, and so on this quantum day, and it is my great pleasure to welcome Professor Buzek, who is with us today at SNT 2025, to present us the second quantum revolution on this day that is named after this technology. So Professor Buzek will make you travel through the history of quantum physics and how relevant it is to the CTBT community. So I expect it will be extremely interesting for all of you and all of us to listen to this talk. And this presentation will also address some questions that you may still have after the first talk we had earlier, the first keynote talk we had earlier in the afternoon from Professor Jensen. And so, Professor Buzek, I do not want to take too much of your time, so I invite you to the podium, and thank you for being with us, and thank you for sharing your insight with us.